then Naksha, you can also start yours. Great. So it's very nice to have Emily Nardoni from IPMU giving our symmetry seminar today on probing anomalies of non-invertible symmetries and symmetry TFTs, or with symmetry TFTs. Take it away.
Okay, thank you very much for the nice invitation. So today I'll tell you about probing anomalies of non-invertible symmetries. So non-invertible symmetries, of course, have a long history, especially in 2 dimensions, and more recently, there's been somewhat of an explosion of activity in higher dimensions. And many of these developments, of course, have been discussed in this nice seminar series. Now, for ordinary symmetries, TFT anomalies, as we all know, provide really useful constraints on our quantum systems. And today I'm going to discuss some very modest aspects of how this picture might generalize in a useful way for non-invertible or categorical symmetries. And this is work done. This is based on this paper from last month with my really fantastic collaborators from whom I've learned a lot, Justin Kaidi, Gabi Zafrir, and Yunshin Singh. Okay, so a modern characterization of generalized global symmetries is to view the global symmetry as being implemented or equivalent to the set of topological defect operators that implement the symmetry. And this is really useful for thinking about generalizations to the traditional notion of a global symmetry. So the classic example, or now at least classic example, is of a continuous Q-form symmetry, call it GQ, with a conserved associated conserved current. Then by exponentiating the conserved current, I get a conserved charge operator, and by integrating the conserved current over a codimension Q+1 submanifold of d-dimensional spacetime, I get a conserved charge operator, and then by further exponentiating this charge, I get a generally topological operator that depends on this codimension Q+1 submanifold. This operator is labeled by the element of the symmetry group, and of course the manifold on which it's defined. And we should think of these operators. These are the operators that implement the symmetry, and we should think of them as the version of the unitary operators that implement symmetries in quantum mechanics. And of course, a very important point is that they only depend topologically on these submanifolds. So in particular, continuous deformations of the manifold that don't change its topology or don't pass operator insertions leave it invariant. And of course, I've written some explicit formulas here for some continuous symmetry, but these also exist. These symmetry operators also exist for finite symmetries and for generalized global symmetries. So these symmetry defects, or I might call them symmetry defect or topological defect operators, they act on local operators that are charged under our symmetry group. So if I have some Q-form symmetry, it acts on local operators that are defined on Q manifolds. So for example, a zero-form symmetry acts on local operators, local point-like operators. And then basically linking my symmetry defect with the local operator implements the symmetry and tells me how my local operator transforms. Now, for traditional group-like symmetries, these symmetry operators satisfy the group multiplication law, which in terms of our symmetry defects or topological defect operators corresponds to the fusion of defects. So fusing to defects, which are labeled by group elements G and G prime, leads to a defect labeled by the composition of the two group elements, and similarly, fusing an operator or a topological defect with its inverse gives the identity or the non-operator. Here I'm drawing pictures that are easy to draw for line operators. So for example, zero form symmetries in 2 dimensions, but of course this generalizes to general dimensions and general Q-form symmetries. So this leads us to the natural generalization, which is to relax this condition of invertibility and consider a more general categorical structure for these defect operators that is governed by a fusion category or a higher fusion category rather than just a group. So in this case, I can consider the fusion of symmetry operators, which can yield a sum of other operators, of other defect operators in my theory, where the sum is over the fusion coefficients, which tells me about junctions between 3 defect operators. And when I have this more general category structure, I lose invertibility in the sense that some of these defects are no longer going to have an inverse. So okay, so it's of course a very natural and interesting question to ask how everything we know and love about groups and can utilize to learn things about quantum field theories using group-like symmetries extends to more general non-invertible or categorical symmetries. And my goal today is to discuss a set of easy to compute observables that will constitute a sufficient condition for an anomaly or a Tuft anomaly of a non-invertible symmetry. And so for the rest of this talk, I'm going to start first by reminding you about the useful picture of Tuft anomalies for invertible symmetries. Then I will discuss how this picture extends to the case of non-invertible symmetries or categorical symmetries, and how we can use the Sim TFT to accomplish our goal and probe the anomalies of non-invertible symmetries. And then I'll give some examples in 4-dimensional gauge theories that implement these ideas. Okay, great. If there aren't any questions, please just shout out if you have questions. Otherwise, I'm just going to keep going with part 1, which is Tuft anomalies for invertible symmetries. Now, suppose I have some quantum field theory in d-dimensional spacetime with, for now, invertible global symmetry G. I'm going to switch between like G and C for global versus for global symmetry, group-like symmetry versus categorical symmetry, just when I'm trying to emphasize one versus the other. Now, if my global symmetry has a Tuft anomaly, I say that my global symmetry has a Tuft anomaly when there is an obstruction to gauging this global symmetry. So the useful perspective here is to couple my system to background classical G gauge fields, call them. Call my background field A, and so for example, for a continuous symmetry, this is the classic A wedge current type term in the action. And if I cannot couple to the background field in a G gauge invariant way up to the addition of local counter terms that depend on my background field, then this signals the presence of a Tuft anomaly. So in particular, if I have a TFT anomaly, my partition function for my QFT, I'm calling it T, would transform under a G-gauge transformation by this phase where the argument of this exponent is a local functional of the background gauge field and the gauge parameter that labels the gauge transformation. And crucially, when there is an anomaly of this form, the gauging is ambiguous. So I might try to gauge my global symmetry by appropriately summing, making my background gauge field dynamical, and then summing over all the gauge and equivalent configurations. But of course, if my partition function can change under a G gauge transformation, then this summing procedure is ambiguous, and I can't gauge the symmetry. Of course, I was saying a lot of this in the language of continuous group G, but of course, it holds for finite G as well. For finite symmetry group, turning on this background flat connection or flat gauge field A is equivalent to inserting a network of G defects on my space-time manifold, where gauge transformations correspond to changes of basis of this network, which are captured in part by F symbols in my for my gauge group or for my symmetry group. Then gauging the finite symmetry corresponds to fixing a triangulation of my of this network, and then summing over all the configurations. Then I have an anomaly if this is not invariant under different changes of bases of the network, in which case I would get a phase from the change of topology of the junctions. So this is what I mean in the case of finite global symmetries. Now, the TFT anomaly of my global symmetry is naturally defined by anomaly inflow from from one higher dimension. So what I can think of is extending my d-dimensional QFT by one dimension, where my d-dimensional quantum field theory lives on the boundary of this higher d plus one dimensional manifold. And in this picture, the anomalous phase of my quantum field theory is canceled by this invertible topological quantum field theory that lives in the bulk, and which I'll refer to, for lack of a better term, the anomaly field theory. So then I would say in this language that my boundary quantum field theory is a relative quantum field theory. And the main point is that the partition function of this anomaly field theory, this anomaly TQFT, is exactly constructed so that under a G-gauge transformation, it precisely cancels off the anomaly of the boundary theory, so that the combination of the two, of the partition function of the boundary theory and the partition function of my anomaly theory, is invariant under the G-gauge transformation. So a classic example of this, which we all know very well, are local anomalies associated to the chiral action, chiral G action on fermions, so chiral fermion anomalies in even dimensional spacetime. So these are encoded in an anomaly polynomial, which is a d+2 form characteristic class, and satisfies the descent relations, which relate it to basically the action of my anomaly theory, or the inflow action. So this anomaly polynomial is the boundary term of a Chern-Simons theory of the variation of a Chern-Simons theory in one higher dimension from the quantum field theory I have in mind. So, for example, for a U1 anomaly in 4 dimensions, my inflow action would be 5-dimensional. It would be of the form A wedge dA, and the descent relations would give me my anomaly polynomial. So this is a very familiar example, but I really want to emphasize that, of course, we know that we can have anomalies in all dimensions and in purely bosonic theories, and in general dimensions, they're captured by, in general, SPT phases in this picture. Okay, so why do we care? Well, first of all, primarily, Tifft anomalies are preserved under continuous deformations of my quantum field theory that preserve the G global symmetry. And so, therefore, anomaly matching between UV and IR, or before and after continuous deformations, is a powerful constraint on renormalization group flows. So, for instance, one statement you can immediately make is that any theory with a non-trivial anomaly cannot flow to a unique, trivially gapped vacuum with no long-range degrees of freedom. Okay, so now we want to ask how this picture might extend to the case of non-invertible or categorical symmetries. So suppose that my quantum field theory of interest in D dimensions has a non-invertible symmetry associated to some higher fusion category, call it C. And for the purposes of this talk, I'm going to really exclusively be focusing on finite non-invertible symmetries. So you can assume that my non-invertible symmetries are finite in this whole talk. Well, what does it mean to have a Tifft anomaly of a non-invertible symmetry? Well, I define the Tifft anomaly as an obstruction to gauging. And so, of course, we can still have a Tifft anomaly, i.e. obstruction to gauging. And what I mean by gauging is really what I meant in the case of quote unquote traditional or invertible finite G, which is I can fix a triangulation of my space-time manifold and sum over all of the defect configurations, where now I'm summing over the defects that implement the non-invertible symmetry or the categorical symmetry. Of course, many questions, however, might come to mind. So first of all, what is the background field that couples to the fusion category, to the categorical symmetry? So I don't know. I don't really have a notion of what it means to couple a non-invertible symmetry to a background field. This is an interesting question. Furthermore, is there a picture of anomaly inflow by coupling to a bulk topological quantum field theory? Well, presumably yes, but I don't really know how to write down the anomaly field theory. This becomes pretty unclear how to explicitly write something down for this non-invertible case. Okay, so so if I'm not sure how to write down my anomaly theory and I'm not sure how to have some background field picture, how do I actually characterize the anomaly? Well, we do have some definitive characterizations, especially explored in 2 dimensions. So in 2 dimensions, the existence of an anomaly is equivalent to the lack of a so-called fiber functor, as was described by these authors. And even more recently, these authors have looked at this higher categorical perspective on looking for or proving things about fiber functors for 2 categories. And this is great, and this classification program is great, but it can be a little difficult to probe in a given theory that I care about, maybe, or to determine whether or not this fiber functor exists. And so our main result, which I'm going to tell you about for the rest of the talk, is really modest. It's a sufficient diagnostic for the existence of a TFT anomaly for a general non-invertible symmetry. And our diagnostic is going to come from computing correlation functions in what's known as the symmetry TFT. So, okay, so
Emily,
what is
a question? So just to clarify, you are asking the question if I can perform any kind of gauging of this categorical symmetry. So you want to find it. You want to find a diagnostic such that no gaugings are allowed.
Yes.
Right.
Yeah, that's right. So, I mean, more generally, of course, I'd love to answer all of these questions. But yes, our main result is just going to be some sufficient diagnostic where if it's true, then I know that I have then I know that I have an obstruction to gauging the non-invertible symmetry.
I mean, so if I just take a group symmetry and I look at this fiber functor definition, for example, there are fiber functors even when you have anomaly, because you can gauge some subgroups on which the anomaly trivializes. Right. So there is one question whether I can gauge some subsymmetry of the symmetry, and there is a question of whether I cannot have any kind of gauging at all. So I just want to clarify, you are addressing the second point, right? So you will say that a G with an anomaly won't be ruled out because there might be some subgroup on which anomaly trivializes.
Good. Yes. So yes, that's correct. So I mean that I will consider some G or some C, and if I say that there's an anomaly, I mean I can't gauge that whole G or C, but I haven't necessarily ruled out some subgroup by this. Thank you. Yeah, thanks for the question. Are there other questions before I keep going? Okay, so the symmetry TFT is a topological field theory that's defined in one higher dimension, much like my anomaly field theory from my quantum field theory. And it essentially extends the notion of the anomaly theory in some sense by relaxing the condition of invertibility. So the picture I have is this. I have my quantum field theory, which lives on maybe the boundary of some anomaly field theory, maybe not. Maybe I do or don't have this picture. And I can extend it by opening up an interval in which I have this bulk symmetry, topological quantum field theory in d+1 dimensions. And on the left-hand side of the bulk, I impose topological boundary conditions, and on the right-hand side of the bulk, I impose non-topological boundary conditions. I'll give some more details in a moment, and it's designed precisely so that when I smush the slab, I get back exactly my quantum field theory of interest. So the main comments of why this is useful is, well, first of all, the symmetry topological quantum field theory, or the symmetry TFT, plus this set of topological boundary conditions really capture the full generalized symmetry structure, including for non-invertible symmetries of my quantum field theory of interest. And so this is the full symmetry structure, information about the anomalies, and so on. And secondly, my symmetry TFT is invariant under topological manipulations of my quantum field theory. So this makes it really useful to compute, because maybe I can compute it in some variation of the theory, and then I do some topological manipulations like gauging or stacking with other TQFTs, where it's more difficult to compute, but the symmetry TFT remains invariant. And I want to emphasize, I'm drawing this picture with the anomaly field theory as if I knew what it was for invertible symmetry group, but really this can be defined for general categorical symmetry, as was emphasized by these authors recently. So in a little bit more detail, the symmetry TFT is basically a gauged version of my anomaly field theory. So in the case where my non-invertible symmetry is either in the case where I have a normal symmetry, invertible symmetry, or when my non-invertible symmetry is so-called non-intrinsically non-invertible, meaning that I can basically get to it by some topological manipulation from an invertible symmetry. Then the symmetry TFT is just a Digraph-Witten theory whose action matches the anomalies of my quantum field theory of interest. So I have some BF type coupling between the my gauge field for my symmetry and its quantum friend, and I have some gauged version of the anomaly field theory partition function, and all the fields here are summed over everything in the symmetry TFT is gauged. Then the topological at the topological boundary condition on the left-hand side of the interval, I can impose either say Dirichlet or Neumann boundary conditions for my fields. So for example, I might impose Dirichlet boundary conditions for my background gauge field, which would correspond to some to fixing it to its fixing the dynamical field in the bulk to its background value on the topological boundary. Or I might impose Neumann boundary conditions where I let the field fluctuate on the boundary, or I might impose mixed Dirichlet-Neumann conditions. Then on the right side, I have this sort of non-topological enriched Neumann type boundary condition, where by this sum here, I mean if I have some finite symmetry group, this is a sum over flat connections, or if I have some general categorical symmetry, the sum is really some sum over all of the symmetry defects that implement the categorical symmetry. And so here I'm representing the boundary conditions as states in the Hilbert space of my symmetry TFT. And then this is designed exactly so that when I smush the slab to 0, which I can do because my symmetry TFT is topological, so it doesn't depend on the size of the slab, I get an effective d-dimensional quantum field theory that I started out with exactly in this way. And one of the important points is that the topological defects of my symmetry TFT, so topological defect operators in the bulk of this slab, yield when they're taken to the boundary exactly the symmetry defects of my my boundary quantum field theory. So the way this works is that my bulk operators in the symmetry TFT can be decomposed into basically two sets. The first set is the set of bulk operators that can end on my topological boundary condition. So here on the left-hand side, I'm showing this is the left topological boundary condition. And so I have some operators in the bulk that are labeled by p-dimensional submanifolds of my d+1 dimensional bulk. And some of these operators can end on a p-1 dimensional locus on the topological boundary. These I'll call belonging to set A, or I'll draw them in red. And so they're associated to the topological boundary condition. The other set of operators, which I'll denote by blue color or call by set B, are the set of bulk operators in the symmetry TFT that can end on a boundary operator. So this first set in red are the terminable operators, and the second set in blue are the non-terminable operators on this topological boundary. And so in particular, my bulk operator can end on some boundary operator that is defined on some p-dimensional submanifold of my boundary. And so I can label the bulk operator that ends on it by exactly the element of my, or by exactly the defect that it's ending on. And then the important point is that it's exactly these boundary defects that give rise to the my symmetry group or my symmetry category of my quantum field theory upon shrinking the slab. So let's do some quick examples just to illustrate this point. So an easy example is take a 2D quantum field theory with Z2 zero form global symmetry. This is just a completely invertible non-anomalous example, which is generated by some defect line in the 2D QFT. Let's call its background field A. Then the symmetry TFT is just some V2 gauge theory. And if I impose, and I would impose Dirichlet boundary conditions at the topological boundary that set the dynamical gauge field in the bulk equal to my background gauge field on the boundary. This symmetry TFT, this V2 gauge theory with no digraph Witten twist, has 4 topological line operators. One is the electric line operator, which is like the Wilson line for the in the bulk, the gauged A gauge field. I also have the magnetic type line operator, which is defined in terms of the dual or the quantum A hat gauge field in the bulk. And I have the operator, the line operator, which is the fusion of these two. And so evidently, according to this Dirichlet boundary condition, this electric line operator can end on the topological boundary, since this just sets the gauge, since the boundary condition just sets the gauge field to its background value. While meanwhile, the magnetic line operator and the fusion of it with the electric line operator do not end on the boundary. Instead, they can end on exactly the boundary symmetry defect, which implements the Z2 zero form symmetry of my boundary quantum field theory. Another example, invertible and non-anomalous, is let's say 4D SUN Yang-Mills theory. This is a higher dimensional example, but I'm just going to draw everything as if it were lower dimensional to make the pictures better. So SUN Yang-Mills, 4D SUN Yang-Mills has a center symmetry, which is a ZN one form symmetry, and it's generated by some operator, which is a surface operator in my 4-dimensional quantum field theory. And let's call the background 2-form gauge field B in this case. So in this case, my symmetry TFT is a 2-form ZN 2-form gauge theory. With so it just has again this sort of like BDC type coupling, and on the right hand side I have my non-topological boundary conditions. On the left hand side I impose Dirichlet boundary conditions for my background gauge field. In this case, much like the last case, I have various topological operators in my symmetry TFT. I have surface operators which correspond to the surface like the Wilson surface associated to my B gauge field, and the kind of TIF surface associated to my quantum or dual C gauge field. And one of them is terminable on the boundary with these boundary conditions, and one of them is not. This one ends on exactly the symmetry defect for the boundary theory that implements the boundary ZN one-form center symmetry. Okay. So hopefully we're all comfortable with how this partitioning works. So so now let me state the main observation. Suppose that we can gauge our categorical symmetry. So suppose it is anomaly free. Then gauging the categorical symmetry changes the topological boundary conditions, but leaves the symmetry TFT unchanged, as we've already said. So when I do this, the left topological boundary is now going to be a condensate of operators in my category, in my symmetry category. And in particular, for each boundary operator that corresponds to one of the symmetry defects implementing the potentially non-invertible symmetry, there's going to be a corresponding bulk operator that ends on this boundary operator. And because of the gauging, this operator should move into the terminable group. Okay. Now,
I think there's a question from Ken about the previous slide.
How can you distinguish two form fields? Oh, good. So so here on this slide, I'm just so indeed these are both two form gauge fields, or two form ZN valued gauge fields. I'm being a little glib in how I'm writing things, and I can view this action as setting as basically setting the other one to be to have ZN valued holonomy and be flat. And so I've just denoted like little b as the background gauge field for my my boundary one form center symmetry. And then when I in this gauged symmetry TFT, I also have the associated quantum symmetry, which I'm denoting as being associated to the two form field C. So hopefully that answered the question. If not, please ask again. Okay. So, okay, very good. Suppose we can gauge it, then some operators are going to move between these groups, and in particular, the operators that correspond to the symmetry that was gauged should move to the terminable class. Now, topological operators in the terminable class have trivial link invariant in the bulk. This is because these are topological operators in my quantum field theory, and so I can just trivially move them around each other on the boundary. That shouldn't do anything, but moving them around each other on the boundary corresponds to some braiding operation in my bulk symmetry TFT. And so when I do this, because I said that, and so I do this for consistency, I should have that correlation functions of these two bulk operators shouldn't give me any sort of extra phase. They should basically just give me, I shouldn't get a phase from doing this sort of braiding operation. Okay, this leads us to our main observation, which is that if our categorical symmetry is anomaly free, then for each boundary operator that implements the categorical symmetry, there must be bulk topological operators with trivial link invariance. Or said another way, and maybe a more powerful way, if one cannot find a representative operator in the bulk symmetry TFT that has trivial link invariance, then the associated categorical symmetry is anomalous. And this is up to equivalence relations among operators. So this is really a simple and straightforward observation that now I would like to use to probe the anomalies of QFTs, and I'll make some comments in a moment. Yes, is there a question?
Yeah, can I ask concretely how this observation works? So let me take a two-dimensional theory with a permutation group symmetry S3, permutation group of 3 elements. So then how, and this can be anomaly free. Now, what would be the map from the boundary operators, which are S3 elements, into the bulk operators, which are now representations of S3 and representations of some subgroups inside S3?
Good. So the statement is that the bulk operators that end on my symmetry operators that implement the S3 on the boundary should have trivial link invariance. So I would compute correlation functions of these bulk operators. I'll do some other examples in a moment. Maybe this will make it become clear. So I would compute correlations of these bulk operators exactly like this, and I shouldn't get a phase, and that would, so I should say that doesn't necessarily tell me that my symmetries are anomaly free, because I've only posed a sufficient condition that I've only imposed a sufficient condition, and I can't probe every anomaly with these correlation functions. But if I had found that the braiding is of these bulk operators is non-trivial, then I would have definitively diagnosed an anomaly. I hope that makes sense.
No,
maybe it'll become clear as I go through some examples.
Okay, sure. No, I'll wait.
Oh no, please go ahead.
No, I'll wait for the examples. I was asking about examples. Yeah.
Okay. Yeah, please ask again. I see there's some discussion in the chat. Should I look at that, or should I keep going?
I think it's clear, but maybe Cyril has a question because he's unmuted. Maybe.
Oh no, sorry, my bad.
No problem. Okay.
Sorry, I also have a question. One second. So is this supposed to work only if U is also an invertible symmetry in the bulk, or for every type of? Because in MTCs, talk about commuting Frobenius algebras, which are a bit more complicated.
Yes. So this didn't. So this diagnostic didn't depend on the symmetry being like non-invertible versus invertible, and of course I could also have cases where like non-invertible operators in the bulk symmetry TFT become invertible on the boundary. This diagnostic could be used in all of these cases. So as long as I can compute these correlation functions, I can use these diagnostics. And so in a moment, I'll show some examples both for non-invertible and invertible symmetries of using the diagnostic. Yeah, thank you. Okay, so before I go further, let me just make some comments that immediately need to be made. So I really want to emphasize this is a sufficient and not necessary condition for a non-trivial anomaly. And so in particular, as we'll see in a moment, this can't probe every type of anomaly. For example, it can't probe one form symmetries in 3 dimensions. And that example is a problem of codimension, just because of the codimension of the defects in question in the associated symmetry TFT. Okay, and another comment is that this is strictly weaker than the fiber functor condition, which was posed by Thorngren and Wang, and then like also like is being just discussed in other cases above 2 dimensions. So this is strictly weaker than that. However, it has the upshot that it can be very straightforward to compute especially when the symmetry TFT is so-called non-intrinsically non-invertible. So in this case, if the symmetry TFT is basically a digraph-Witten theory, the link invariants are easy to compute. And so this can be a nice and also kind of physically intuitive diagnostic of the anomaly in these cases. And also, I want to emphasize, we can, of course, go beyond links involving just two lines. Like we can probe anomalies involving more than just two operators. So, for example, if I want to probe an anomaly that involves two operators in my symmetry TFT, I would want to compute link invariance with two components. And so then the condition is that closed manifolds M, say M1 and M2 with dimensions P1 and P2 are able to link in general Q dimensions. So I'm looking at some symmetry TFT, which is in like D+1 dimensions. So then Q is D+1. If the dimensions all satisfy this relation, so if P1 plus P2 plus 1 equals to Q, so in this case, I can compute the linking of the manifolds M1 and M2. This is given by some integral over the Poincare duals of the Seifert surfaces, which are like the surfaces that bound the manifold, and which give basically the number of intersections between the Seifert surface of the first manifold with the second manifold. This is maybe best shown with an example. So for example, I can look at lines in 3 dimensions, then like line operators in 3 dimensions, then this shaded area of this line is supposed to indicate the Seifert surface of this line, and then I can count that the linking of this configuration, which is the Hopf length, is 1, or I can consider linkings of other configurations with higher linking number. If I want to probe anomalies involving 3 operators, then I need to look at 3 component links. And in this case, I have a more general condition. Again, this is some condition on codimension so that the manifolds can link. In this case, I'm going to have 3 types of different linking invariants that I might compute. And for example, if I want to compute this for lines in 3 dimensions, then one of these types of linking invariants is probed by the Borromean ring configuration of the lines. Okay, so that's the idea. Now let's just see some examples. So first, let's just do a purely invertible example in 4 dimensions. I'm going to just do a version of the 4D SUN Yang-Mills example I did before, but now I want to do an example with an anomaly that we can probe with this diagnostic. So let's take gauge group SU4. Just for simplicity, I'm going to take the rather than SUN, SU4. And we'll look at 4D SU4 Yang-Mills. And this is exactly the case we studied on the previous slide, except now I'm going to gauge a normal subgroup, a Z2 normal subgroup of my Z4 one-form center symmetry. I'm doing this so that I end up with a theory with a mixed anomaly. So when I do this, my global symmetry group is Z2 times Z2 one form times Z2 one form, where one of these is my quantum or dual symmetry, and one of them is what's left over from my original Z4 center symmetry. And so, for example, I can give these background gauge fields associated to these symmetries names. I can call them B hat and B twiddle. So this gauging procedure changes the topological boundary conditions in the symmetry TFT picture, although it doesn't change, as I've emphasized, the symmetry TFT itself. So basically, I'm just changing the topological boundary conditions on this side the topological boundary so that I have mixed Neumann and Dirichlet boundary conditions. And in doing so, I have to attach this anomaly field theory, which cancels off the mixed anomaly between these two Z2 one-form symmetries. So this anomaly, this 5D anomaly action, anomaly inflow action is exactly canceling the mixed anomaly of this gauged theory. And then all of this is manufactured so that when I shrink the slab, I get back my gauged 4D SU4 Yang-Mills after gauging the Z2 one-form normal subgroup and coupled to now my two background two-form gauge fields. So before I listed some of the basic surface operators in my theory. After gauging, what happens is the surface operator labeled by little b reduces on the bound now belongs to this B subclass and will reduce on the topological boundary to precisely the surface operator that generates my Z2 twiddle one-form symmetry. Meanwhile, my other topological operator, the one that I labeled by C before, reduces on the topological boundary to exactly the surface operator that generates the quantum Z2 one-form symmetry in my QFT. Meanwhile, as anticipated, the operator which generates the subgroup of the one-form symmetry that I've gauged, in this case it's UC squared, moves from the B subset to the A subset. It becomes terminable since it has to, because it reduces to the gauged Z2 one-form symmetry defect. Okay, so again, nothing's changed in my symmetry TFT. This is the same set of operators I was considering before, but they've moved around whether or not they're terminable, and we can track what they generate on the in our boundary quantum field theory by just checking what happens under the boundary conditions we've imposed. And so now I can compute the bulk correlation function between this operator that reduces to my Z2 twiddle one-form symmetry on the boundary and my operator which reduces to my Z2 quantum one-form symmetry on the boundary. And I can compute and check that I get -1 to the linking number or linking variant between the two surfaces that that these operators are defined on. And so the fact that I have a mixed anomaly in this theory is being probed by this link invariant. So this is a purely invertible example in 4 dimensions. Now let's move on to a class of non-invertible examples with anomalies. So let's consider our d-dimensional quantum field theory with some symmetry group, which starts out as invertible. So I'm going to consider a class of examples where I have some ... that I don't care about, and some invertible symmetry H, and some ZM zero form symmetry, which I'll label by the background field A. And I'm going to consider this class of examples where this subgroup H and ZM have a mixed anomaly, and where the finite ZM symmetry has a self anomaly. I'll give an explicit example on the next slide, but this is an interesting class that applies to, for example, 4D SUN adjoint QCD, as well as n equals to 4 super Yang-Mills. So in 2D, it applies to the abelian Higgs model. So it applies to many QFTs that you might be interested in. So okay, so this is all invertible so far. Step 1 will gauge the this symmetry H And in doing so, we promote this finite symmetry ZM to a non-invertible symmetry, which is implemented by a non-invertible defect. This was discussed in work by several authors that I think I show on the next slide. So again, I'm starting with some QFTT in the symmetry TFT picture with symmetry with invertible symmetry G, and then I gauge so that I change the topological boundary conditions. I have some sort of anomaly field theory on the other side, but I don't really know how to describe it. And now when I collapse the slat, I'm going to get the gauged theory with a categorical symmetry C, because I have this non-invertible defect that satisfies their various fusion rules. So that's step one. Step two, we'll see that this non-invertible symmetry is anomalous. This is, I think, in some sense obvious and expected. It basically follows from the fact that we started with a theory with an invertible symmetry that had a self-anomaly, and then we gauged in such a way that it's promoted basically to a non-invertible symmetry, and this non-invertible symmetry indeed still has an anomaly. And the way we can probe the fact that it has an anomaly is by computing link invariance in the symmetry TFT. So we'll look at these bulk operators in our symmetry TFT that end on our non-invertible defect, and we'll compute their correlation functions with each other. And the fact that there was this self-anomaly that manifests in the symmetry TFT is going to give me some non-trivial phase that depends on the linking of the surfaces. So let's be a little more specific with our example. Let's take 40 SUNC adjoint QCD, by which I mean 40 SUNC gauge theory with some number NF of adjoint Val fermions. Its symmetry group is indeed exactly of this form. I have various continuous symmetries that aren't going to play a role in this discussion, like the SUNF symmetry and so on. But I also have my ZNC1 form symmetry, and which is unbroken because my matter is all in the adjoint of the gauge group. And I have a Z2NFNC axial symmetry, which is the what's left over of my U1 axial symmetry after the APJ anomaly. So 40 adjoint QCD has an anomaly action, which captures in 5 dimensions, which captures the fact that this one form center symmetry and Z2NF and C finite axial type symmetry firstly have a mixed anomaly, and secondly, the axial symmetry has a cubic self anomaly. And so this is the action. I've written it explicitly for even and C. I just have to write basically like B wedge B or B cup B in this first term instead for odd NC. Okay, so from this I can write down my symmetry TFT and write down my list of defect operators in my symmetry TFT. And these include, firstly, a set of line and surface operators that are terminable on the topological boundary. These are electric type operators that are basically, this one is the Wilson line associated to the Z2NF and C background gauge field. And this is like the Wilson surface associated to the background center symmetry gauge field, the two form B gauge field. And I also have maybe call it magnetic type surface and volume operators, which belong to this class B that end on boundary defect operators. And these are basically of the form like Wilson or Tuft surface and volume operators for my quantum A hat and B hat fields in the symmetry TFT, except these actions wouldn't be gauge invariant on their own. I have to supplement them with some TQFT action that depends on my gauge fields in order to make this a gauge invariant operator. And precisely because of this TQFT action, these magnetic type operators are non-invertible defect operators in my symmetry TFT. They're non-invertible in the bulk symmetry TFT, but on the boundary, they reduce to invertible operators that implement my, my global symmetries. Okay, so that's the scenario before I gauge. Now let's gauge my center symmetry, which promotes my, this basically changes the global form of the gauge group. So gauging the ZNC, or in this case, I'm talking about Z4. Sorry, I should have put, oh no, I'm doing general NC here, never mind. So I gauge my ZNC one form center symmetry, which gives me a PSUNC gauge theory, which is PSUNC adjoint QCD. This gauge theory has a quantum ZNC one form symmetry, and also now, as discussed by these authors, has a non-invertible defect, which satisfies fusion rules that look like this. So this first fusion rule is telling me that my defect is non-invertible. It gives me the fusion of the defect with its conjugate gives me a sum over the operators that implement the quantum ZNC one form symmetry. So this is the piece that's telling me this is non-invertible effectively. So what happens to my operators in my symmetry TFT? Well, they move around. The magnetic U-B hat operator moves into my terminable subgroup, and my and that's of course because I gauged the symmetry that it generates. And my electric UB surface operator moves into my non-terminable subgroup, where now the two operators that reduce to the boundary symmetry operators are this operator reduces on the boundary to my quantum ZNC one form symmetry generator, and my UA hat operator reduces on the boundary to precisely this non-invertible symmetry defect, which is a volume type operator. And I can, again, check all of this explicitly with the symmetry TFT and just checking what happens to the operators when I impose the correct boundary conditions. So then I can ask whether or not this non-invertible symmetry is anomalous. And the way to probe that is to probe correlation functions involving this this defect in the bulk, which reduces to the non-invertible symmetry defect on the boundary, and that's this UA hat operator. So I can compute correlation functions of this form, and I would get this. So this is a correlation function with 3 UA hat operators, which will probe the self anomaly. And indeed, I get a non-trivial phase that goes with the linking number between these 3 surfaces. And this is interesting that this phase is non-trivial for all NC greater than 1 and NF greater than or equal to 1. So we conclude from this analysis that 40 PSUNC adjoint QCD has an anomalous non-invertible symmetry for all values of NC and NF greater than or equal to 1. So one comment here is that if I didn't know about the non-invertible symmetry, there would have been special values of NC and NF for which the invertible symmetries were non-anomalous. So basically, that's looking at this term here, this NC squared minus 1 term over 6NC, which for some cases, for some values of NC is trivialized. But these cases are ruled out because we know about the anomalous non-invertible symmetry for all values. Okay, so I see I'm running a little short on time, so I'm almost done. I want to end with just a couple of comments. So my first comment is you can ask how knowledge of this anomaly I just described can be used to think about the anomaly matching between UV and IR for this class of theories. And so, for example, let's consider NF equals to 1 adjoint QCD, so N equals to 1 super Yang-Mills. Of course, NF equals to 1 adjoint QCD has enhanced N equals to 1 supersymmetry. In this case, which is, of course, it's very well known that the now, in this case, Z2NC zero form symmetry is spontaneously broken to its Z2 subgroup by the Gaugino condensate. This leads to NC gapped supersymmetric vacua in the IR and domain walls supporting 3D Chern-Simons theories that couple to the background gauge field for the center symmetry match the mixed anomaly that we were just discussing between the zero form and one form symmetries, this A cup contraigen square of B type anomaly. So then you can ask, how is this self, as was, for example, asked by these authors recently, how is the self anomaly matched with this domain wall picture? And schematically, you can think about asking this question in the symmetry TFT picture that I've been advocating. So in this case, I think about starting on the top of this diagram with my N equals to 1 SUNC super Yang-Mills theory. It has an anomaly. So that's the purple is the anomaly field theory. And I expand it out into my symmetry TFT with my Dirichlet boundary conditions on the left-hand side and my non-topological boundary conditions on the right-hand side. And then I can consider the RG flow to the IR where everything is completely gapped and topological. So what happens is my right-hand side in the IR, my right-hand side boundary flows to a topological boundary condition, which is mixed Dirichlet and Neumann boundary conditions for the background gauge fields. What happens in this RG flow is that now, because of these topological boundary conditions, one of my line operators can end on both topological boundaries and becomes a topological order parameter upon smushing the slab for the Z2NC zero form axial or R symmetry, which labels the NC vacua. Meanwhile, the defect, which the volume defect, which I said reduces to the boundary Z2NC defect in the UV, in the IR exactly matches onto this domain wall. It becomes the domain wall that hosts the Chern-Simons theory, and you can see this completely explicitly by just checking what happens to the this defect with its explicit action. And I should say that a nice holographic perspective on this sort of story with the symmetry TFT and N equals to 1 super Yang-Mills was studied by these authors recently. So then we've already understood the matching of the mixed anomaly by the domain wall due to the domain wall theory in the IR. And then the simple comment I can make on top of this now with this picture is that the fact that the domain walls and the junctions saturate the self anomaly, like the cubic self anomaly for my Z2NC R symmetry, is exactly related to the fact that this bulk topological operator has a non-trivial triple link invariance. So because this is the operator that in the bulk that reduces to my domain walls, basically the fact that I get braiding when I move the boundary operators around each other is exactly associated to the fact that we have this cubic self anomaly for the Z2NCR symmetry. And I kind of explained this schematically, but I think it would be interesting to understand exactly how this works in detail. Okay, so I'm probably really out of time. So I'm just going to this is my last slide. I'm just going to quickly say that another example of a 4D quantum field theory with this type of non-invertible anomaly is some special cases of n equals to 4 super Yang-Mills. So in particular, at special values of the complexified gauge coupling, when subgroups, certain subgroups, discrete subgroups of the SL2Z duality group can have a self anomaly. And if at these points, the theory is mapped to itself under the discrete subgroup, then this would be a normal Twift anomaly for an invertible symmetry. But if the theory is not mapped to itself under the discrete subgroup, then we can combine it with gauging of a one-form symmetry to obtain a non-invertible symmetry. And then the self-anomaly from the pre-gauge theory will imply an anomaly for the non-invertible symmetry post-gauging, which exactly takes the form that I was just discussing in this class of 4D gauge theories with this type of anomaly. And so you can check certain values of the complexified gauge coupling and of the gauge group that realize this sort of non-invertible anomaly in n equals to 4 super Yang-Mills. Okay, so I'll stop here and I'll just summarize that what I told you is that much like for ordinary symmetries, Twift anomalies of non-invertible symmetries are a useful tool for constraining the dynamics of quantum field theories. Linking invariance in the symmetry TFT can provide a diagnostic of Twift anomalies for generalized symmetries, and these are simple to compute in many examples. Examples of theories with anomalous non-invertible symmetries include 4D adjoint QCD and n equals to 4 super Yang-Mills, and tracking the defect operators in the symmetry TFT across RG flow can lead to interesting insights into anomaly matching. So I think there's several interesting future directions. Maybe I'll just lead this slide up and end here. So thank you very much for your attention.
Okay, thanks very much. Other questions? You can just unmute yourself or raise your hand, put it in the chat. Maybe I can come back to the question that Laksha asked before, which is you were saying for, I think all your examples are non-intrinsic.
Yes.
And then you were saying essentially this pulling topological defects into the bulk is straightforward, but I think all the examples you've considered are abelian. So have you thought about non-abelian groups? And example that he was mentioning was S3.
Yeah, so I think it's a good question. And
because you were saying basically whenever it's essentially like a group like invertible symmetry, like for example back S3 or 2-back S3, then the bulk theory is trivially constructible, and I'm not sure I completely agree with that.
Okay, so the bulk theory is So what I mean is that when the so when I can obtain the symmetry TFT by some topological manipulation from an invertible symmetry, then typically it is straightforward to construct the symmetry TFT. And so in this talk, I focused on these types of examples because of
But
which,
it is
you know,
invertible,
like,
right? If I have just an S3, say zero form symmetry acting, it's a group.
yes, that's an invertible symmetry. Yes, yes. So I would have to think. Okay, so the answer is this should be doable, and I haven't done it.
Okay.
So yeah. My answer is I think that should be doable, and I haven't done it. But thank you for the question. Yeah.
Okay. Are there any other questions?
Yes, I have a comment about this intrinsically non-invertible symmetry and how one might consider anomaly for that. And but I wonder if can draw. If I need to draw a little bit. Let me try to see if I can.
Sorry. So the question is. Go ahead.
Xiaogang, your question, I think we couldn't quite hear the last part of the question.
Yeah, I have a comment on this future direction, this intrinsically non-invertible symmetry, how to get a result that. But I try to draw. Can I share the screen and draw something? Hello?
Hello?
Yeah.
Yeah, so you should be able to, if there are no other questions about the slides, then we can do that. So I think your question was related to the intrinsically non-invertibles.
Yeah.
And how to see the anomalies there.
Yeah.
So I think if I recall the construction of KOZ, the second paper of KOZ, but maybe Yunqing is in the call too, is then basically they construct sort of gauging of a sim TFT, so it ceases to be like a digraph fitting theory directly.
Exactly. So basically, there is a way to gauge this intrinsically non-invertible symmetry in a sense. This intrinsically non-invertible symmetry can be described by this so-called local fusion category, and whose center gave rise to the bulk. This bulk is the symmetry TFT.
Yeah.
And if you insert an invertible domain wall in the symmetry TFT, that's basically like adding this make this gauge theory into a diagram-Witten theory, but for non-invertible symmetry. It's a let me try to share my screen. Because,
so I'm just trying to see. You should be able to share the screen
let me try to
it's allowed for everyone.
Okay,
So I'm not sure.
Can you see my shared screen?
I can see your screen now. You can actually just switch it over on your on the settings, view options, and then you can switch from Emily's to Xiaogang's screen. Yeah, I can see the two red lines.
Yes.
So this R is a fusion, so-called local fusion category describing intrinsic non-invertible symmetry. This local fusion hierarchy category can also be viewed as roughly as a fusion hierarchy category with a fiber functor. That's describing anomaly-free theory. And this stacking, this M is a center of R, and this stacking is a gauged version. Unfortunately, I don't have a pen, so I'm just sure. This stacking is a gauged R.
Okay.
So this is using symmetry TFT to describe the gauged intrinsic non-invertible symmetry. So this is like a gauge theory for R. And then if you insert an invertible domain wall in the middle, then that became kind of a Dagravitten-like theory. That's make it is a cosine twist. Then the boundary of this can be viewed as a intrinsically anomalous R symmetry. It's yeah, very roughly do you have this structure? Yeah. So the tricky thing is that we don't have background field, so gauging is tricky. But using this stacking with the inverse, so the arrow is also important. I think this configuration gave you gauge the theory. Then inserting this invertible domain wall automorphism gave you the Dagravitten theory. Yeah. So that's a comment I want to make. Yeah.
I see.
So there's
a
version. Yeah, there's a version of that.
Okay. Yeah. Thank you for the comment.
Yeah, any other questions? I don't now. All the screens have disappeared. Okay, let's thank Emily again. There's a question here by Ken Kikuchi. Did you remind me the definition of TFT? I thought you said it is a generalization on only field safe and non-invertible case. That's not quite true, but that would be, yeah. Anyway, let's thank you again. Then there can be more informal discussions. All right, thanks very much. I'll stop the recording.
Yeah.
Thank you.